It's a pleasure for me and great honor to present a talk at this conference dedicated to the Jubilee of Ludwig. And so I will try to follow the exact title of this conference, Mathematical Physics, Past, Present and Future. So I will start with some general formulation of the method. For me it's past, but I don't expect that everybody are well known or well acquainted with this approach. Then I will say a few words about, actually I will do it more or less at the beginning, a few words about present, some applications, I mean have in mind in infrared, gauge invariant infrared regularization of Young-Mills theory, and I will finish with some speculations which are not yet finished, but nevertheless possible development of this approach. Okay, so I want to say that at the end of 60s there was a revolutionary breakthrough done in quantization of non-abelian gauge theories by two groups. One group here in St. Petersburg, it was Ludwig Fadeev and Dieter Popov, and the other late Bryce DeWitt in the United States. Okay, but the idea which was behind this approach, developed, for example, by Fadeev and Popov, was already illustrated here. So if you have some... in Moscow, I'm sorry. Nevertheless, if you have some gauge theory, so then you have some orbits of gauge group, and then you have some section. And in physical words, this means you choose some gauge and do quantization near this gauge. Of course, if you do it properly, then all the machinery like Fadeev and Popov ghost, etc., arises. But the point is that in non-abelian theories, there is no unique choice of this gauge. This fact was noticed by Gribov, and so got a name of Gribov ambiguity, etc. Well, and then Zinger, who considered the general situation, formulated a general no-go theorem, that there is in any theory, gauge theory, non-abelian gauge theory, does not exist a gauge which is universal for every field.
On sphere.
Yes, this is true. This is true.
So Minkowski space is different.
Okay. No, this is true. Yeah, I agree. Well, nevertheless, there was a big activity, mainly by Zwanziger, which somehow tried to use this phenomenon. But what I want to show that one can, in fact, we know by experience that any no-go theorem in field theory did not really mean that this approach is bad. But they just indicated that in this approach you could not get a good result. You should be more clever and to use some bypass. Okay? Well, and I would say that the same is true here, in my opinion. So I will going to describe you approach which allows to liquidate this non-uniqueness. By the way, if you consider perturbation theory, then of course this choice is unique, the choice of gauge is unique, so there is no problem at all. In perturbation theory, there is no problem. But beyond perturbation theory, and in QCD we need something beyond perturbation theory, there is a problem. Okay, well, let me say a few words about, okay, so it is here, yeah? Page down. Oh no, sorry, page up. Well, let me just to give an idea, to say a few words about well-known example, quantum electrodynamics, or even classical electrodynamics. Everybody knows that in classical electrodynamics, as well as quantum electrodynamics, all observable can be described by tensor of strength, okay, by strength tensor, or curvature tensor, if you wish, okay. But on the other hand, if you consider quantum theory and interaction of electromagnetic field with fermions, then using only F mu nu stress tensor, you cannot formulate local theory. And what is the way out? The way out is to introduce the vector potential, A mu. But vector potential has some unphysical components, namely longitudinal and time-like components, okay? And one should prove that these extra components are harmless, so they decouple from physical excitations. And so I wish to use the same possibility here. I want to say that usual formulation of Young-Mills theory, which is based on Faddeev-Popov quantization, for example, is absolutely good for perturbation theory, but beyond perturbation theory, you should use some other formulation. And it's possible also use in perturbation theory, of course, but nevertheless, it does not suffer from this non-uniqueness which was pointed out here. So, I propose to describe the Young-Mills theory by the following Lagrangian, which looks a little bit complicated, but nevertheless it is easy. Well, this is usual Young-Mills Lagrangian. Yeah, okay. Now I introduce two scalar fields, phi and chi is negative energy excitation. Okay, and then I introduce also the shift. I shift the fields phi and chi by vector m, which is constant. The first by spinor, sorry. It is two-dimensional spinor, which has the first component is 0, and the second component is real constant, okay, m.
Definite metric for what?
Yeah, of course, yes, of course. And definite metric, of course, is needed. Yes, this is true. But nevertheless, I wrote here also alpha here, and alpha, so that means that I shift phi and chi by different values. Phi I shift by m, okay, and chi I shift by alpha m, okay? Yeah.
How is it for this constant spinor? You also have a derivative, right? So the derivative only the gauge potential will compute?
Yes, that's correct. That's correct. Yeah, that's correct. Yeah. So the derivative here is not here, so you have only gauge potential.
So it's just a nice way of writing it.
Yeah, nice way. Okay, but it is easier to write it like this. Well, and you see that alpha equal to 1 corresponds to the removal of infrared regularization. Because for alpha equal to 1, this term disappears, the mass term disappears, and we have the usual Young-Mills theory. But for alpha not equal to 1, we have some infrared regulator, this mass term, okay? But on the other hand, the theory, of course, for alpha not equal to 1 is not unitary. My claim is that I will show that for alpha equal to 1, this big Lagrangian, yes, I've described only part of it, by the way. There is also part which depends also on scalar fields, but B and E are elements of Grassmann algebra. So they are anti-commuting. Why this Lagrangian? Let me just as an indication to show you. So let us consider the not shifted Lagrangian. So without these terms and without this term, okay? Then suppose we have integrated in a vacuum sector corresponding to phi, chi, and B and E, okay? Then integral over phi and chi produces the determinant to the 4th degree, okay? But the integral over B and I produces the same determinant, but to the minus.
I'm confused. How does the longitudinal mode decouple?
Oh, it's wait a little bit. Wait a little bit. It's of course it's not obvious from here. Yeah, but they are okay. For alpha equal to 1, they decouple. Only for alpha equal to 1. Yeah. Okay. So. And this is why this Lagrangian, as I said. But let me now show. I consider the group SU2 just for simplicity, although it's not important. And I consider the parameterization which is similar to the one which is used in Higgs model. Namely, I parameterize all fields, scalar fields, by Hermitian components, phi1, phi2, phi0, and phi3. They are Hermitian components. So I have a complex spinor, as in Higgs model, but it is parameterized by Hermitian components. And the Lagrangian is obtained from the gauge invariant Lagrangian, describing the interaction of complex scalar doublets with the Young-Mills field by the shift. This is shift written explicitly. Okay? So you see that phi is shifted by m, by constant, one component of phi, and chi is shifted by the same constant but with alpha. If alpha equal to 1, that is the same shift, and no mass term exists. However, for alpha not equal to 1, there are infrared regularization is present. Well,
I missed the phi was, so the phi and chi are in joint representation? What are?
No, not adjoint. They are in fundamental representation, like in Higgs model. So the same like in Higgs model. It doesn't matter. One can also choose them in a joint representation, but I prefer more developed formalism, which is due to Higgs model. Well, first of all, let me say that original Lagrangian was gauge invariant. Yes, this is true. That means that after the shift, it's also gauge invariant, but it's invariant with respect to the shifted gauge transformation. Okay? This is just change of variables, nothing else. Okay? And this is non-trivial. So we have, so suppose for the moment that this Lagrangian, it's not yet clear, but let us suppose that this Lagrangian describes really Young-Mills theory. Then let me remind you that there is no gauge, no known gauge invariant infrared regularization. In fact, if you introduce simply mass term, then of course you lose gauge invariance. If you may be more clever and introduce gauge invariant mass term, like using Stückelberg formalism, for example. But then, as was shown in our paper with Ludwig, that first of all, you lose renormalizability, but moreover, you have, even in the second order, you have a different result from the massless theory. So there is no regularization, and you can, of course, use Higgs model for regularization, but then, in the limit, m goes to 0, you have Young-Mills theory, which is massless, and also massless scalar. So no way out. And here you have gauge invariant infrared regularization. But of course it is a regularization, so unitarity is spoiled. So this is correct. But for alpha equal to 1, I will show you that unitarity is restored. Okay? Well, in particular, as I said, the transformation of the field phi plus minus, I introduce the component which are sum and difference of phi and chi is, and you see here that delta phi, of course I can write different fields also, but delta phi is shifted by arbitrary constant, okay? So that means that phi is also gauge field, And that means that for alpha equal to 1, that alpha is gauge field, and that means we can choose a gauge when phi minus equal to 0. You can also choose a gauge phi plus equal to 0, it depends on you. Well, but phi minus equal to 0. And I stress that this field, this gauge is, first of all, algebraic, so there is no differential operator, so there is no ambiguity. On the other hand, it is manifestly Lorentz invariant, okay? And so it is what we wanted. So we really have some gauge which is Lorentz invariant and has no Gribov ambiguity. Well, but of course, when we considered example of quantum electrodynamics and introduced instead of F mu nu the gauge field A mu, then we did not, we pay for that. we pay, but it was in fact benefit. So we benefited that because the new Lagrangian was gauge invariant, okay? In terms of F mu nu, gauge invariance is nothing. Gauge invariance, there is no gauge invariance. But in terms of A mu, gauge invariance is present in the theory, and it is used heavily to prove that gauge invariance is sufficient to decouple excitation of longitudinal and time-like photons, etc. Okay. In this case, we also have additional symmetry, which is supersymmetry. And the supersymmetry transformation is written here. So delta phi is transformed by B, shifted by B. Delta E is equal to phi plus, and delta B is equal to 0. And epsilon is...
That's a BRS symmetry.
It's not... it's not super, it is supersymmetry, but in fact, this symmetry is present without any gauge invariance. So it's, you can call it BRST symmetry, but...
Supersymmetry usually means that it's super Poincare invariant.
This is OSP.
Well, okay, it depends. But it is not, I would say that I would not call it BRST symmetry because it is present even without any gauge invariance. BRST symmetry is gauge invariance, definitely. Yeah. So let me maybe show you that indeed this is a symmetry. Yeah. So look here. So first of all, you see that shift of the field phi and chi does not change this symmetry. Yes. And this Lagrangian was supersymmetric. Indeed, when we shifted phi by b, del mu b, then we have this term which was d mu b, not d mu phi. And the same similar term we have from here when shifted e by phi, okay? So again d mu b and result of shifting e. And the shift of the fields phi and chi does not change this
But
symmetry.
if you also have a supersymmetry where phi plus and e are transformed, and phi minus and e are...
Yeah, phi plus. E is transformed only by phi plus, not by phi minus.
Yes, but you must have supersymmetry here where e and p change the place and phi plus and phi...
For alpha equal to 1, yes, you may do that. But for alpha not equal to 1, the supersymmetry is not here. And this supersymmetry is, in fact, important to prove the decoupling of longitudinal and time-like components. Okay? Well, it's written here, by the way. This invariance, this supersymmetry transformation, plays a crucial role in the proof of the equivalence of the model described by the Lagrangian, which I showed you, to the standard Young-Mills theory. It provides the unitarity of the scattering matrix in the subspace, which includes only three-dimensionally transversal components of the Young-Mills field. I should say that, of course, the notion of scattering matrix for Young-Mills field is a little bit fishy, I would say, because it is infected by infrared regularization. But nevertheless, we want to, well, this object, in fact, it's always accepted in Young-Mills theory, that Young-Mills theory is good in some sense, but we don't know how to work with infrared divergent quantity, okay? Well, in the case under consideration, the massive theory with alpha equal to 1 has no this supersymmetry, and therefore it's not unitary. It may seem strange, as usually the gauge invariance is a sufficient condition of unitarity, and this gauge invariance is present. But here, the formulation is a little bit different, and in particular, usually what you use? Gauge invariance you use to pass from unitary gauge to renormalizable gauge, okay? So you can do it. But here, there is no unitary gauge, in fact. Even the gauge phi minus equal to 0, even in this gauge, there are unphysical excitations. And we should prove that they decouple. And that's what I should do. Okay, so in the following, I think I will consider explicitly the case when alpha equal to 1. So I will show that for alpha equal to 1, I have the same theory as the usual Young-Mills theory. Okay? Well, canonical quantization in the gauge phi minus equal to 0 requires introduction of ghost fields, of course, but these ghost fields are ultralocal, so they do not spoil unitarity. They are ultralocal, local fields, so they don't spoil unitarity. But however, you have another conditions. First of all, we should somehow remark that the condition phi minus equal to 0 breaks the invariance with respect to the symmetry transformation. Okay? Therefore, what does it mean? Okay, there are two approaches. One approach I shall not discuss here, but in my opinion, the simpler approach is the following. So, however, transition from one gauge to the other one may be achieved by gauge transformation. Yes, this is the meaning of gauge invariance. And in the gauge, Coulomb gauge, this one, the effective action is invariant with respect to the super transformation, which was written here. That means that in the gauge phi minus, it also must be invariant with respect to some super transformation. But the explicit form of this super transformation is different, of course. Yeah? And so you consider the action effective action in two different gauges, and in gauge you use the fact that all the action except for gauge fixing term is gauge invariant. Yeah? Therefore, the only difference may arise from gauge fields. So you should have this equation. This is Coulomb gauge, then gauge transformed Coulomb gauge, and it must be equal to lambda phi. So we should find out some super transformation which leaves this invariant. Okay? And when we consider the scattering problem, of course, we are working only in asymptotic states. Our initial and final condition are asymptotic states. So it simplifies our problem. And so, in fact, it's possible to find out a solution for any g, but it is sufficient for us to find out the solution for g equal to 0. And then, if you consider this equation, then you can have a condition for eta. Eta is a gauge parameter, which connects one Coulomb gauge with gauge phi minus a equal to 0. Okay, but you see that phi minus is changed by supertransformation. That means eta is also changed by supertransformation. And this one, you just substitute in this formula the supertransformation of phi. Okay? And therefore, a mu is transformed differently than usual.
There should be derivatives there because there is no mu.
Yes, sorry, there is a derivative. That's correct. I'm sorry, there is a derivative here. You are right, absolutely.
Derivative of everything.
Yeah. Derivative of d mu. Okay. Okay, yes. So, sorry. Yeah, sorry. All right. So, with this reservation, then we see that asymptotic theory should be invariant with respect to this transformation. Here there is a derivative, by the way. Well, and mu is m, actually, in my notations. Okay, sorry. Well, so this is a transformation for a mu. Then this is transformation for phi 0, which is not changed. And this is transformation for e and for e0, okay? All right. Delta b is not changed, okay? This invariance, together with the usual BRST invariance, this is, by the way, we should somehow distinguish the usual BRST invariance, and which is related to gauge invariance, etc., and this one. So there are two commuting charges, q and qb. And the asymptotic states may be chosen to satisfy the condition should be annihilated by q0 and q0b. Okay? QB is a BRST charge, and Q is associated with this supersymmetry. And we want to prove that the Lagrangian, which is written here, okay, so let me show you. This is 7. So this is gauge fixing, which is, in this case, is autolocal. So there is nothing here. But, yeah. So this Lagrangian plus gauge fixing term is invariant with respect to this transformation. So definitely, and we want to show that after the substitution on the asymptotic states, the condition that they are annihilated by QB0 and Q0, we have the usual Young-Mills theory. Okay. These symmetries, as I said, are sufficient to prove, first of all, the renormalizability of the theory, and it was done in our paper with Quadri, Andrea Quadri, and the unitarity of correspondence scattering matrix for alpha equal to 1 in the subspace which contains only three-dimensionally transversal components of the Young-Mills fields. Scattering matrix for alpha equal to 1 acts in a bigger space containing the excitation with negative energy, and of course is not unitary in the physical subspace. So it is really regularization. So let me say a few words about it. So the spectrum of a modified theory, even for alpha equal to 1, includes additional ghost states. So there are a number of ghost excitations. First of all, phi plus minus, phi and chi, B, E, and then of course the usual longitudinal and temporal components of A mu. But there are no, by the way, Fadeev-Popov ghosts, because in this case they are autolocal, so they do not contribute to the unitarity. And physical excitations are three-dimensionally transversal components of the Young-Mills field. Okay? Now, so physical states are separated by this condition. First of all, these are annihilated by the charge which associated with supersymmetry by Noether theorem, and also they are annihilated by BRST charge. Well, it can be done that if you look explicitly at these operators, QB0, this is BRST charge, and this is supersymmetry charge. If you look for those who is familiar with the BRST quantization, then you see that QB0 exactly coincides with the usual BRST charge in the transversal gauge. Phi plus you should identify with the lambda, which introduces the gauge condition, and then you identify Fadeev-Popov ghost C with E and anti-ghosts with B. Okay? This is the first term, and this is the second term. So this corresponds to P transversal and P longitudinal, sorry, and here is A0, corresponds to A0. And the second term, so all these terms decouple, all these excitations decouple. But there is additional excitations here, which are described by phi 0 plus and B 0. Okay? And also the same is true for phi minus and E, because phi minus with phi plus commutator is not 0, and B and E 0 is not 0 also. Okay? So, and this can be proven that this operator Q0 provides the absence in the asymptotic states the quanta corresponding to the fields phi0, b0, and corresponding fields e0, phi minus. Okay? Well, this is usual done in the theory of cohomology, and this is, so you introduce the operator K, this one, which is organized in the same way as operator Q0, but is with a substitution. Instead of B, we substitute E, and instead of phi plus, we substitute phi minus. And any vector which include at least one unphysical states may be presented in the form. If you consider commutator of Q0, anti-commutator of Q0 and K, then you will see that it is a number operator for the unphysical modes, as usual. Okay, and therefore you see that any vector which is annihilated both by Q0 and any vector, sorry, which is annihilated by Q0 has a structure. This term is 0, okay? And this term is Q0 multiplied by some vector. Okay? And this, of course, zero norm vector, because Q0 squared is equal to 0. Okay? So we proved that, first of all, we proved that invariance with respect to this transformation guarantees absence of longitudinal components of ghost fields and also lambda, okay? And this is this charge, conservation of this charge is responsible for the absence in the asymptotic states of phi 0 plus minus and b 0 e 0, okay? Therefore, the only terms which survive are the terms which correspond to physical excitations. So this is the answer to your question, Antti. Yeah, so it is not easy answer, but nevertheless it is true. Okay. Therefore, for alpha not equal to 1, we have a gauge invariant theory. I stress it, emphasize. It's gauge invariant theory which describes massive Young-Mills quanta. But of course it's not unitary in the physical subspace. For alpha equal to 1, we have usual massless Young-Mills theory. So we succeeded in construction of the gauge invariant infrared regularization. Okay? Obviously, the regularization may be used both in perturbation theory and beyond it. Why beyond? Because the gauge does not suffer from groove ambiguity. So you can use this gauge also beyond perturbation theory. Okay, yes, I already finished, but I want to say a few words about possible perspectives, the things which I am working on now. Well, you know very well, of course, that the Young-Mills theory, pure Young-Mills theory, had no solitonic excitations. On the other hand, you know, yes. On the other hand, if you work say on a lattice, then usually people use some kind of solitonic excitations, and they introduce them in some artificial way, I would say. Well, here there is an alternative formulation which introduces some new scalar fields. And therefore, so it's not obvious that there is no soliton excitations here. And moreover, well, I claim, but it's not yet finished, so I'm not prepared to defend this position, that indeed soliton excitations in this formulation do exist. But this is, no, this is still should be checked and completed. Yeah, so thank you.
Questions that you would like to ask?
Well, let me make a small comment on the Gribov stuff. Yes. So we know that, philosophically, that quantum mechanics is quantum mechanics, and we can try to find it from classical by quantization. But quantization is, as I say, art, not science. So in this thing which we have done with Popov, of course, we rely on classical theory, but when we constructed quantum theory, it could be different in a way. It must not. Well, what I have in mind is that, of course, when you introduce ghosts, so instead of determinant, which apparently is difficulty of Gribov, we just put them up. Then we have just a new field theory with a mu, C bar, and that's it.
No.
And there is this, I think it's
so forget that it came from gauge fixing.
Exactly. Yeah, exactly.
That's what you're saying.
So that Ajima, I think it's Kuba.
Kuga-Ajima, yes. Yeah. But what
what's that? You say if you integrate over ghost, you'll get determinant back. But in electrodynamics, if I integrate by Fermions, I'll get also determinant of, with a mu, which is also bad.
No, you had in mind BRST quantization effect. Yeah. Yes, that's possible, but in BRST quantization, you lose gauge invariance from the very beginning. So you consider even classical theory, which is not gauge invariant. It's possible. I don't know of course, but nevertheless, it.
Enough for canceling all this.
If you use, say, Kuga-Ajima, you lose the possibility to pass to different gauge. In one gauge, absolutely, but you lose the possibility to pass to different gauge. Here, it's preserved. So in any gauge, to any gauge you can pass. and of course beyond perturbation theory. The gauge which is allowed beyond perturbation theory. For example, to the gauge phi minus squared divided by some alpha. Okay.
Another
Yeah.
thing that they also, Fadeev and I were playing many years ago, that it looks like the approach when you enlarge the space, introduce more fields, and in the bigger space you have more freedom to do things nice.
Yeah, yeah.
So we called it conversion. Like we
Okay.
did second class constraints converted to first class constraint in a bigger space and so on. So that's very similar to...
Yes, it is similar, I agree. Yes, it is similar.
Bigger
Yeah.
space where you have more...
Yeah. But as I said, we do the same thing even in QED, in quantum electrodynamics, because we enlarge the space. Instead of F mu nu, we consider the space which contains also longitudinal and time-like photons, but then we also gain gauge invariance, and we can prove.
And I'm sorry, one more comment. Where is the one? There is a 1969 paper by Fadeev, as you know very well, in Hamiltonian approach.
Yeah.
So if you rewrite and restate Gribov problem in Hamiltonian approach, it's not a problem. When you consider the bigger space, which is now the E and A, the electric field and the vector potential, then in that space the Gribov problem is absent.
No, I don't quite agree. Yes, the Gribov problem may be avoided, but at the price you pay is the loss of gauge invariance.
Well, not relativistic.
You are in Hamiltonian approach. It's not manifest relativistic invariant.
But nevertheless, it is. And here you cannot pass to some other gauge. To some other gauge you cannot pass.
No, in Hamiltonian approach.
No, because you will need some determinant which does not exist for us.
That means that Coulomb gauge is still bad. Of course, Gribov was right, but there are other gauges when the Gribov problem is not.
No, there is no. I don't know such gauge. If you know, please indicate. Okay. Okay.